colleague Neil McGregor from Ricardo.
Hello.
Welcome to our fourth LinkedIn Live session for the Stealing Motive vehicle. Stealing Motive is our vision of concept vehicles that will help us achieve net zero emissions by the target date of 2050. And if you've had an opportunity to join us previously, you learned a little bit about these vehicles. And today, we're going to discuss and focus on sustainability and how our concept vehicles put us on the pathway for net zero emissions. So let's get into it. Just as a reminder, who World Auto Steel is, we're the automotive group of the World Steel Association, headquartered in Belgium. And these are our member companies. They represent 18 of the world's largest automotive steel producers. You can see their logos here. And we're a research organization. We conduct engineering projects with esteemed engineering institutes and organizations such as Ricardo to evaluate the applicability of today's modern steels in new vehicles. And to remind you a little bit more about the Stealing Motive program, Stealing Motive design is shown right here in this slide. This is the exterior styling for our small concept. It's a 4-passenger vehicle. And we also have a larger stretch version of this. That's a 6-passenger vehicle. The 4-passenger is more of a inner city commuter vehicle. The 6-passenger could be city to city, city to airport, as it's got expanded occupancy and luggage space. So as we developed this vehicle and the concept architectures, we had various attributes in mind because we wanted to make sure that these vehicles could be deployed in mass and scaled very quickly to meet the needs of the industry for emissions reduction. And so you can see in the Venn diagram these different spheres representing our targets. On the left, you see, or on the right, you see comfort. We knew we needed to make sure the vehicle was comfortable and easy to access, a low step-in height. We have these scissor doors that open up to a 1 meter width to allow easy access into the vehicle. And we needed to make sure that the vehicle was safe because in order to have comfort in taking these type of journeys, the passengers wanted it to feel safe. Also, we needed to address the affordability component to make sure that the vehicles were affordable to use, but also affordable to produce. And then finally, on the left, we see the sustainability sphere, and we knew we needed to address all factors that contributed to life cycle emissions to make sure that we were optimizing those for emissions reduction to help get us on these targets. And so those overlapping areas, we term that, and our chairman of World Auto Steel coined it, future mobility that only steel can make real. So today we're going to focus on sustainability, that left sphere, and that's what this is right here. This is a life cycle perspective, kind of a circular economy of a vehicle from cradle to grave. And Neil, you want to make a couple comments about this chart?
Yeah. So this chart really describes the approach and the considerations that we took for the life cycle assessment of the Stealer Motive vehicle. So we looked at all aspects of the Stealer Motive vehicle, all the way from its inception, from its manufacturing, all the way through to the end of life. And we did that all the way through the project. So during all of the key design stages, all of the key decisions that we made about the Stealer Motive vehicle, we considered all of these parts of the vehicle life cycle. So just to touch on each one of these briefly, so during the manufacture of the vehicle, what some of the most significant contributors to the embedded carbon of the vehicle is the steel and the manufacture of the steel itself. So we looked at decarbonisation of steel and also the battery. The high voltage battery has a significant contribution to the overall production CO2. So we investigated that as well. We optimized the vehicle design, so we minimized the weight of the vehicle. We optimized the material utilization and the manufacturing processes, again, to minimize CO2 emissions at production. And then through the life of the vehicle, we looked at the real world driving cycle of an autonomous vehicle that has an impact on the energy that the vehicle uses, with it being autonomous. And also we considered the future decarbonisation of the electricity grid, and looked at different regions and contributions of that. And then finally, the end of life and the different methodologies that are applied through the LCA process. So a lot of individual investigations and studies went on all the way through the Steel Automotive program, and we'll try to show some of the contributions of these to the final vehicle solution through the following slides.
Okay, great. Thanks, Neil. So, yeah, you did a nice job of setting this up. So Neil was the lead from Ricardo on our program on the development of these concept vehicles, chief engineer at Ricardo, and myself and Neil and our vast team of engineers that worked on this, we had some direction to Ricardo and Neil's team as to, we wanted to make sure that we optimized and reduced the thicknesses associated with the steels that were applied to the body structure. And of course, having this vast portfolio of advanced high-strength steels at very, very high strength levels, up to 1900 megapascals, allowed us to reduce thickness even in with very specific crash members. So we were able to do that. Of course, if you reduce the thickness of the material, you're producing less material, which means you're producing fewer emissions. Neil mentioned higher use of more efficient manufacturing processes for the components. So if you use these advanced fabrication processes, instead of engineered scrap at 50% for conventional stampings, you can get up to 90% efficiency, meaning only 10% scrap. So that means you're producing less steel, right? So the emissions are falling in those areas. And then, Neil, we also had several applications where we were able to benefit from part integration, which meant that we reduced the manufacturing operations associated with those additional parts, but we reduced the number of parts in those components. And so again, fewer production emissions. How about the last couple, the traditional battery box and then the existing infrastructure? What would you say about those?
Yeah, so our battery concept is quite innovative in itself, in that it's we call it coverless, so it doesn't have a traditional housing like a conventional battery box does. We use the body in white and the body in white floor essentially as the top cover of the battery. So that eliminates some material and reduces weight. And if you reduce weight and reduce the amount of material you use, then you reduce the amount of embedded carbon in your vehicle. So the battery in itself, it gives us some good cost and weight savings, but it also gives us a good contribution to low life cycle CO2 as well.
Yeah, and the fact that we're able to use existing manufacturing infrastructure certainly speaks to the deployment and scalability of these vehicles, but we're also avoiding investment and the construction of new equipment, new dies, new presses, et cetera, right? And all the emissions that would be associated with that. So it helps us avoid the introduction of new emissions, correct?
Yep, absolutely right, George. Yep.
Yeah. So then, if we step back to that life cycle chart that Neil started with there, I think he mentioned that the steel industry is a contributor, right? The amount of embedded carbon in the steel that's produced is one of the factors of the total life cycle emissions. But we're happy to report that the entire automotive steel industry is working hard on greening and decarbonization activities. Here's an example chart that shows a combination of DRI, direct reduced iron, and the EAF process, which is a process that heavily uses scrap. And by doing that, we're able to reduce the emissions associated from production of virgin steel material or virgin iron. And so this, I think the chart would show, if we look at the technology roadmap, that the automotive steel producers should be 100% green by 2035. And that means that the emissions associated with the manufacturing of each kilogram of steel are going to continue to fall pretty dramatically, which will help contribute to the emissions targets that we're seeking. But just to put it in perspective, steel is already the most efficiently produced material on the planet. We're about 7 to 17 times lower in emissions from the production of each kilogram compared to some of the alternative materials that are used in body structures, including aluminum, and where we look at carbon fiber or some of the plastics, as well as magnesium. So we benefit from that already really impressive emissions production performance. So then let's talk about the use phase carbon. Neil, you want to comment on these?
Yeah. So yeah, for an autonomous vehicle, we kind of had to think about the use phase quite differently compared to a kind of a human operated vehicle. So firstly, obviously, one of the biggest contributors to CO2 during the operational life of the vehicle comes from the electricity that charges the vehicle, the electricity that comes from the grid. And then the carbon content of that is obviously dependent on the renewable content. So whether the electricity comes from solar or wind or other renewable sources. So we took that into consideration in our LCA calculations. We looked at different scenarios and forecasts of renewable energy, and we did that for different regions. Obviously, the Steel Automotive is a global vehicle, so we considered and we analyzed the operational cases in China, Japan, India, Europe, and the US. So we looked at the different sensitivities or operating the vehicle in those different regions. And like I said earlier, we did a lot of work looking at the decarbonisation of the battery. Obviously, there are, similar to steel production, there's a lot of effort going into decarbonising the battery cells and their contribution to CO2. So we took an estimate on that, some of our own Ricardo internal studies, and applied that into the LCA calculations, estimating that there's a 72% potential reduction in greenhouse gas emissions, comparing a battery from 2020 to 2030 and beyond. And then the final point on there is actually the operation of an autonomous mobility as a service vehicle. So these vehicles will only really become effective at reducing CO2 during the life cycle if we increase passenger occupancy. So we need to get more passengers into these vehicles, reduce the number of journeys, and then that reduces CO2. We also considered extending the vehicle life. So Steel Automotive is designed to operate up to 500,000 kilometers. With that, we get the vehicle operates longer. So we need to manufacture less vehicles over a particular lifetime. And then finally, with it being autonomous, we've got the ability to control the speed and the energy that goes into the vehicle through computational power, and use vehicle to vehicle and vehicle to infrastructure type connected technology. So the vehicle knows where it is, it knows where traffic lights are, so it can manage its speed a little bit better than a human operated vehicle. And so we took that into account, and I think we saw up to about a 20% improvement in efficiency over a drive cycle for Steel Automotive. So considering all of these aspects into the operational phase of the vehicle, again, that went into our overall vehicle LCA calculations for Steel Automotive.
Thanks, Neil. Those are great points. So, so you can tell by looking at these charts that we've tried to address all the factors that really contributed to the life cycle emissions by our kind of deployment scenario in that 2030 to 2035 timeframe, and aligned with our target for deployment are other aspirational targets by cities and by regional areas. The greening of their electric grids, for example, as well as taking advantage of the technology roadmaps that show us great improvements in battery efficiencies, et cetera, by that same time frame, 2030, 2035. What happens over time with various different scenarios of deployment of these steel automotive concepts. So, Neil?
I think we're losing George a bit on the.
Yeah, we lost you for a second. Yeah. 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 So, you want to just take us through this walk down real briefly, Neil?
Yeah, so essentially this is a snapshot, a waterfall of the potential different scenarios of implementing the different technologies from Steel Emotive. So on the left-hand side, we've got a representation of a present-day internal combustion engine vehicle operating today. And then on the far right-hand side, where we've got the bar SEM3, that is the relative life cycle CO2 per passenger kilometer. So we use a slightly different metric there. That is sort of the operational potential of Steel Emotive when it's in full operation in 2030, 2035, with all of the aspects of the carbon reducing parts of elements of the vehicle when they're in operation. And then the two steps in between there are kind of stepping down from that. Obviously, when it's unlikely that we're going to be able to apply all of those metrics and scenarios in one single go, and there's going to be a gradual phased in of these CO2 technologies, and that's what the two bars there represent. So the first one is kind of 37% reduction of embodied carbon compared to a conventional ICEV. So that's switching to electric. SEM2 is introducing some of the Steel Emotive measures, and then the bar on the right-hand side is with all of the Steel Emotive carbon reducing measures completely considered in the calculations.
Yeah, one thing that I'd like to mention is, the choice of the autonomy for this vehicle. I thought that was a smart choice because as we look into the future, if you remove the driver, you create additional space for another occupant, right? And
Yep.
in order to really achieve the dramatic reductions in emissions that you show all the way to the right, we're counting on being able to fill up these vehicles with at least 3 passengers, right? Because
Yep.
that's where we really have the opportunity to reduce the number of vehicles on the road.
Yeah, absolutely. Like I said earlier, these autonomous vehicles really excel in their potential for decarbonisation by increasing the occupancy. So, we're aiming to increase occupancy from, I'd say a present day taxi human operated vehicle where the average occupancy is something like 1.4 passengers per journey. We're looking to get in excess of an average of three passengers per journey. So with that, you're increasing the number of passengers in the vehicle, you're decreasing the number of individual journeys, and then you're reducing the number of vehicles on the road. So that's a significant contributor to kind of overall vehicle life cycle CO2 emissions reduction with these vehicles.
Yeah, that's great. And failed to mention the title of the slide, but we went to Ricardo Energy and Environment and Energy after our first wave of engineering to say, okay, we're really confident that we've taken a lot of measures to reduce the footprint of these vehicles and to really help put us on that path to net zero. But could we take a look at some very specific cities and what their targets look like and how relevant Steel Emotive is to those cities, helping them achieve their emissions targets? And so we looked at, with their help, really, they picked 2 cities, London and New York City, and we'll just share with you the results of London. But so Neil just gave us a nice summary on this slide. And then this slide really overlays the net zero emissions targets from the City of London, that red line that you see there, and then how Steel Emotive under various scenarios helps put us more closely to that path and the realization of those targets. Anything you'd want to add, Neil?
Yeah, I mean it's just great to kind of see how Steel Emotive and the implementation and the rollout of Steel Emotive and mobility as a service vehicles could actually impact an actual city. So the previous graph was kind of, maybe more hypothetical, the vehicle in isolation and looking at sort of passenger CO2 kilometer metrics. This is kind of real world numbers, looking at the City of London and their projected or their current CO2 emissions and their projected targets. And then, as George said, the yellow line there is a scenario of a potential rollout, an implementation of these vehicles such as Automotive, and it shows how, through the progressive rollout of this up to the year of 2040, how that can significantly impact a city such as London. It can impact their overall CO2 emissions. So it was a great study to kind of wrap up the program to see how exactly a vehicle like Automotive could actually have a real world impact on a city.
Thanks, Neil, for that summary. That's great. And when we saw this output from Ricardo E&A, we were quite impressed and quite satisfied, right? That
Yeah,
we
it was
picked the
nice.
right targets, and that realistically we were able to make an impact like this. So that's it. That's our summary and our story today on sustainability from the Steel Motive concept perspective. We're quite pleased that considering all of the contributing factors to emissions reductions opportunities, that we've clicked off all of them. We've addressed them all, and you can see that when you do that from a holistic or comprehensive perspective, you can really help achieve these targets that seem so ambitious and daunting. So, Neil, thanks for participating again with us.
Pleasure.
If you get a chance, all of our previous sessions are available on our World Auto Steel YouTube channel. Check us out. And thanks for joining us today. Everybody have a great end of your day and a great weekend.
All right. Thanks all.